So today we will be discussing something more about interference, and I would mention here that the content for this lecture actually belongs to the chapter on interference by John E. Grevenkamp from the book Handbook of Optics, Volume 1. So many figures presented here have been taken from this book. So I sincerely acknowledge and thank the original contributors for that. Now let's continue our previous discussion on interference. And in this lecture we shall be talking about interference of different cases. So first case will be plane waves. I mean, what happens when two plane waves interfere? How would be the interference pattern? And what happens when a plane wave and a spherical wave interfere with each other? What will be the interference pattern in that case? We shall then be talking about a concept of temporal beats and coherence. Why we need two beams to be coherent for observing a stable interference pattern on a screen. So in your lower classes you are already just taught that the coherence or two sources must be coherent to result into a interference pattern. But now we will be seeing that is that a mandatory condition, or I mean interference pattern will not the phenomena of interference will not happen if the two sources are not coherent. That is what we will try to answer in this present presentation. And also we shall be then talking about two methods of obtaining coherent beams of radiation, and these are wavefront and amplitude division. So I think that would be the part of the contents which we will be covering in today's lecture. Remaining is going to be the part of upcoming lectures. Say we will be seeing in detail how we can obtain interference pattern by amplitude division. What is this Young's double slit method? All these things we will be seeing in our coming classes. Now let us try to study the interference of two plane waves. How does two plane wave interfere with each other, and what type of pattern the interference of two plane waves results? Let us consider this diagram where we are having two beams of plane waves which are traveling this way. So their wave vectors are, say, k1 and k2, and I hope you know that this wave vector is representing nothing but the direction of propagation of the beam. So first wave vector or the first beam is propagating along this direction, and these are two plane waves. So plane waves means their wave fronts are nothing but the simple planes, right? And this is representing the wave fronts. So the distance between the two wave fronts is what? I hope you know. That is nothing but the wavelength, correct? We have discussed it in the previous class. Same is the case here. Now let us assume that these two beams are traveling in xz plane. So notice it. The two beams, suppose, are traveling in xz plane, and we have actually, so this is where these two beams will interact with each other, and that is where we can observe the interference pattern on a screen. So let us assume that we have placed a screen here which is perpendicular to this plane, means which is perpendicular to xz plane. So suppose we have taken a big, say, rectangular screen, and that has been placed in a plane perpendicular to xz plane. So what is the plane of the screen? that is going to be XY plane. I hope you could visualize that. So plane of the screen will be XY. So it will be something like, okay, I am taking a notebook and placing it along this x-axis and perpendicular to XZ plane, right? So that is where the screen is placed, and we want to study the characteristics of the the interference fringes obtained on the screen. So I hope the problem which we are going to discuss is clear to you conceptually. Now, okay, let us assume that this first beam is making an angle theta 1 with z-axis. So this is your z-axis, and second beam is making an angle theta 2 with the z-axis, and r is some arbitrary vector in the real space. We will be looking at its utility in the coming slide. Now, since the two waves are plane waves, and we know how to write down the electric field component for plane wave, so this is given by this expression, where A is amplitude, that is a constant thing in place of plane wave, and what if it is a spherical wave, then it will be A upon R. So since we are dealing with two plane waves, these both are plane waves, so the electric field component can be written to be like this, and this is general. Actually, this is a general expression for electric field of a wave which is traveling in any direction, say R. But in this case we are saying, okay, the direction of propagation is this for first one, and this is direction of propagation for second wave. So in that case, and considering the geometry of our setup or of this experiment, the electric field for the two waves in general can be written to be like this, where I represents subscript corresponding to, say, first. I is equal to 1 represents this first beam, I equal to 2 represents the second beam. So electric field for first beam will be E1 at say different points in x, y, z in space and a particular time. This will be equal to omega t minus k z into cos theta I. So theta 1 in that case, so cos of theta 1, and in second case it will be sine of theta 1 for second component. Now this expression looks like something which came from heaven, right? Let us try to see in detail how does this expression results as per this geometry. So okay, before I go to the detail, and we will also assume, or to keep our life mathematically simple, we will assume that, okay, the point where we have placed the screen refers to z is equal to 0. So that is why we can put z here to be equal to 0, and then life will be further simple. But first let us see how does this leads to this in context of our present problem. Then we will be obtaining this phase difference and all. So let us first focus on how we can write down the electric field. So this is the problem which we are discussing. So we have our xz plane. In xz plane, plane wave is incident like this, and this plane wave is making some angle, say theta. Let me say a single case, then we can replace it with theta 1 and theta 2. So let us assume that this plane wave is making an angle theta with z-axis. So that's our situation in the previous figure which we have discussed. And r vector is something like this, some arbitrary vector in the space. Fine. Now k vector can be written to be like this. This k vector, it will be having three components, something like, say, kx I cap, ky j cap, kz k cap. Sorry, this should have been kz. So please correct it. Okay. So kz k cap. It should have three components. But what is interesting, and what will be the values of those components? So kx will be equal to k sine theta. I hope you should see from here what will be the x component. Let us first see z component. So kz is equal to k cos of theta, means z component of this vector will be k cos of theta. Well, and what will be its x component? That will be k sine of theta, because these x and y are 90 degree to each other. That's a basic thing, I think. What about ky? Ky is 0 because the wave is traveling in xz plane. So there is no component of this wave vector along y direction. Correct? Similarly, r is some arbitrary point in the space. So let us write down its coordinates, or the r vector, to be like this: xi cap, yj cap plus zk cap. So that k vector dot r vector, which has to appear there in the electric field, can be obtained from the dot product of these two vectors. So if you take the first one, I dot I, this will give you kx, which is nothing but this k sine kx is nothing but k sine theta into x, and ky is 0, so that is okay. Kz into z, so this should be cos theta into this should be k cos theta into z. Yes, that's it, correct. So k into cos theta into z, that's this term is coming from the multiplication of say z components, and this term is coming from multiplications of x components. So this will be k sine theta into x, this is coming here, and this is k cos theta into z, which is coming here. So k dot r vector is equal to k into z into cos theta plus k into x into sine theta. Correct? Okay, let's go back to the previous now. I hope you have noted it. Let's come here. So that's what we have written here. So for first wave, this is equal to a e raised to the power iota omega t. This term is as such. So k vector dot r vector will be nothing but k into z into cos of theta 1 for first case. So minus sign is because this is minus is sitting here, as it is as if the wave is traveling along positive r direction. So here now it is traveling along this particular direction. See, this r is any arbitrary point in the space. Okay. Okay, so this is minus this. So we have just substituted that value. I hope that is clear to you. Now, for simplicity, what we are saying is, okay, let us take z to be 0. Means the screen, we can always take reference of our z-axis at the point where we have placed the screen. So z is equal to 0. In that case, this term will go to 0. Correct? So we will be having two waves whose electric fields will be, say, E1 is equal to a e raised to the power iota omega t minus kx sine theta 1. Correct? I should have put it, I don't know if I have put it somewhere. No. So you note it in your notebook. That will be good. I'm sorry. I should have put those terms here, E1 and E2. But okay, you can do that yourself. So I'm just dictating it. So E1 should be equal to a into e raised to the power iota omega t minus k into x sine theta 1. That's your E1. Similarly, what will be E2? Electric field associated with this second wave or second beam, that will be equal to a e raised to the power iota omega t. This, because screen is at 0, so z is equal to 0. So now we are trying to describe electric field on various parts of the screen. That's what is the meaning of putting z is equal to 0. So at various points on the screen, we are trying to write down the expression for electric field, and it is those two electric fields at various points of this screen which will lead to the interference effects. So E2 will be equal to, I hope you have written that, a e raised to the power iota omega t minus k x sine theta 2. So the only difference will be sine theta 2. Now what will be the difference in phase of the two electric fields which are interacting at any point on the screen which is located at z is equal to 0? The difference in phase will be, so iota omega t is common in both the E1 and E2. So that is not going to contribute to the phase, right? Both, we are assuming that both the waves are of same frequency. Fine. In that case, the phase difference comes from these two terms, and that is equal to k into x sine theta 1 minus sine theta 2. And you know what is k? K is nothing but 2 pi by lambda. So we just substituted its value. So delta phi, the phase difference between the two, is equal to 2 pi by lambda into x times sine theta 1 minus sine theta 2. Simple. This we already have done. So let me move to the next. Now we know that intensity of the resultant wave at a particular point in the space as a result of superposition of two electromagnetic waves can be written to be by this expression, where you know what is gamma? Gamma is fringe visibility, and this delta phi is that phase difference which we just now obtained for the set of two plane waves. Now in this present case, okay, we are again making one more approximation, that let us assume gamma is equal to 1, means fringe visibility is 1. Now you go back to our previous lecture and try to see what is the meaning of fringe visibility. So fringe visibility 1 means that dark fringes are completely dark, means intensity is 0 there, and bright fringes are having intensity equal to I max. So we can assume that to be an ideal situation which we expect. So in that case, this we can take to be 1. So therefore Ixy, now xy, remember this is crucial here, intensity at any point. So I hope you remember that our screen was kept in xy plane. If you want me to show that figure again, okay, the screen has been kept in xy plane. So this is xz plane, xy plane is perpendicular to this xz plane. So we are wanting, or we are trying to write down the expression for intensity of radiation as a result of superposition of these two plane waves in on a screen which is located or placed in xy plane. Now this we have just put the value of delta phi, which is equal to this one. Let us try to see the analysis, a little analysis of this. That okay, what will be the nature of the interference fringes, you would say, which are obtained on the screen. Let us assume, okay, intensity is equal to, say, I naught is 2a square. You can obtain the expression for I naught. This will come out to be 2 times a square, where a is the intensity or amplitude of, sorry, a is the amplitude of individual source. So a square is intensity of individual source. So let us assume both have same amplitude, so that is fine. Both are having similar intensity, so I naught will be equal to 2a square. So this is how we can try to see this. This refers to the one plane wave coming, this is second plane wave coming, and the two, this is now, remember this is your xz plane, means the plane of propagation of the waves. And this is representing the resultant interference pattern which is to be seen on the screen. So now this is xy plane. So on screen what you see is something like this. You see the linear fringes on the screen. Now the question is, okay, why the fringes are linear and what will be the width? Say for example, if you want to find out, so these are bright fringes, a white color, black color refers to the dark fringes. So the question is, okay, why these are like okay, these are like linear bands, and what is the width? So the question is, first let us ask the first question, why they are linear. Okay, before we move to the fringe periodicity, let me answer it here. Now if we see the intensity as a function of x and y, we will see that on right hand side only x appears, there is no y on the right hand side. What does it mean? As you increase x, so this is origin, you go towards this side on x-axis, you will be seeing this is a cos function. So this is a fixed value. Theta 1 and theta 2 are fixed by how the waves have been incident. So theta 1 and theta 2 doesn't change. They are fixed. Their direction of propagation is fixed with respect to z-axis. So this is fixed. So as you increase x, so this is a cos function. You know, cos function is periodic. right? So what will happen? You will be, now let us, you can put x is equal to 0 here, so this will be 1, so intensity will be highest. So at x equal to 0 you will be finding a bright fringe. Then you can find out, if you move, now you can find out that okay, what values of x will be the minima and what values of x will be the maxima. Just substitute different values of x here and you can find out. So that is why. And y means, what does it mean is, okay, at x equal to 0 there is a maxima. Now whatever value of y you take, it will always remain maximum for that particular value of x. Means these are going to be like linear bands, they will be straight lines in xy plane like the ones shown here in the figure. Now the question is, what will be the distance between any two bright fringes? We can say like, okay, fringe width or periodicity of the fringes. This is given by this number. So you can see, okay, this is the one bright fringe, center of this bright fringe. This is center of this another bright fringe. So the distance between the two is given by this expression. P, periodicity, you can say fringe periodicity, is equal to lambda by 2 sine theta. Okay, I'll be coming to this. Let us see this in the next slide. Why this number is equal to this one. To see this, I mean to find out what is fringe periodicity, we know that intensity actually is periodic by virtue of this function. If you go to the previous slide, the intensity is periodic by virtue of this function, right? This is a fixed number, so it is periodic by virtue of this function because cos is the periodic function. Now finding fringe periodicity is nothing but just looking at what will be the periodicity of this function. And I hope you have done it in the previous class. I have taught you that how to find out periodicity of such a function. So as a sincere, what I suggest is that you pause the video here and find out the periodicity of this function yourself, and then I have done it for you in this slide as well. Then you check your answer with what I am going to speak next. Okay, so so we had to find out the periodicity of this function. So you know what is the definition of periodicity means. Okay, if I change x with x plus p, what I should find out is the same function. Means what is the definition for periodicity is f of x plus a is equal to f of x, right? So I am doing the same thing and I am writing periodicity with p. So this should be equal to the same one, right? So if I simplify this, then what does it mean? Means 2 pi x by lambda this thing is as such here, means 2 pi p by lambda into sine of theta 1 minus theta 2 should be equal to 2 pi. This means what should be p? P should be equal to lambda divided by sine theta 1 minus theta 2. Just these things cancels and you take p to this side and lambda goes to that side. That is simplification you can do. And okay, now you would have seen, okay, that was from the previous slide. This is equal to lambda upon 2 sine theta. Why is it not this one? Because if you see the geometry of this incident beams, this has been taken as a special case of this one. What is the special case? Okay, before I move to the special case, there is another way of doing this. We could have done it another way also. That okay, we know the phase difference between the two waves is given by this, and if for constructive interface, what should be the phase difference? That should be 2 pi, isn't it? If I put this 2 pi on this side, I can rearrange the things and find out from there what should be periodicity p. So p should be equal to lambda upon sine of theta 1 minus theta 2. Okay, let's move back to the special case. So theta 1, in this case what we are saying is, okay, theta 1 is equal to minus theta 2 is equal to theta. So we are saying, okay, this is first beam making some angle theta, this is second beam making equal value of angle but in the negative direction, that is minus theta with z axis. So this is the special case, and when we put the two, P comes out to be equal to this value. That's the periodicity. So what is P? And this is the special case, low angle. I mean, if theta is to be very, very small, so sine of theta can be taken to be theta. This is low angle approximation, so periodicity will be lambda upon 2 theta. We can put it here. So this is something interesting. Okay, whenever two plane waves interfere with each other, they results in the fringes of this kind on a screen. Linear fringes. You find out straight line like fringes of this specific fringe width. I hope this is clear to you. Now let us move to the next case of plane wave and spherical wave. I mean, here what we want to do is, what happens if a plane wave and a spherical wave produces interference pattern. So what is the geometry for our experiment is something like this, and they leads to something very interesting. So now what is the geometry is, suppose we have a point source here and it is emitting the spherical waves like this. I hope you can visualize them in this diagram. So it is emitting spherical waves, and the wavelength of those waves is lambda. And along with this, we also have a plane wave coming like this. So plane wave is coming like this, right? So this is a point source. It is emitting spherical waves, and there is a plane wave as well, which is coming like this. So this is the direction, wave vector for the plane wave. Spherical wave will have wave vector like k vector here like this. It is radially outward always. So spherical wave have a wave vector which is radially outward to the sphere. Now the interesting thing is that whenever such two waves do interfere with each other, they leads to the formation of such circular fringes. Now why does these circular fringes appear? So that we will be seeing now theoretically in more detail. And for keeping our life simple, okay, we are assuming that our observation plane, so in the similar way, so one is a spherical wave coming this way, one is plane wave coming this way, both are interfering, and we are putting a planar sheet, or we can say that as observation plane or a screen on say this point at say z is equal to r. Now let us write down the expression for electric field of a spherical wave. This is something interesting. For a spherical wave, I think I haven't put it here. Okay. Spherical wave. I hope you remember that previous expression. So that was a upon r e raised to the power iota omega t minus k dot r. It was k dot r. So for a spherical wave, r is actually a point at say surface of the sphere. R is a point on surface of the sphere, and for a surface of sphere we say, okay, suppose it has coordinates x, y and z, then we can say that r I can write down to be something like the magnitude of r is x square plus y square plus z square, and z we have already chosen to be capital R, say any distance. So therefore this is nothing but that k dot r. So this is magnitude of r, and it was a dot product, so we have taken cos of theta to be 1. Why? Because as I already told you that for a spherical wave the wave vector is radially outward, right? So means k vector and r vector makes an angle 0 with each other. So that is why this is just k into r. So k, the magnitude of the wave vector, which depends upon lambda of course, and r, which is nothing but, so rho square here is nothing but x square plus y square. Rho square is x square plus y square. So rho is x square plus y square under root. So this will give you nothing but this term is nothing but x square plus y square plus z square, and z square is nothing but r square. So that's it. So this is k into r. So this is representing electric field for a spherical wave. Now we are using some approximation here and applying binomial theorem to this part. So for applying binomial theorem, let me take r outside. and if I take r outside, then this will be 1 plus say rho upon r whole square and raised to the power half. So by applying that binomial theorem, you can easily find out that this expression turns to this value. And of course here we have neglected the higher order terms. Now the question is, okay, what is the meaning of neglecting higher order terms? Meaning of neglecting higher order term is that rho upon r is very small. It is very small in comparison to 1. What does that physically mean? Means rho here is x square plus y square. So suppose this is your xz plane, the plane in which the waves are traveling, correct? And the xy plane represents the plane of observation, or that of our screen, xy plane. So what we are assuming here is that, okay, this rho, that is you can say, okay, radius of a circle on the screen is very small in comparison to r. Means the size of the screen is very less in comparison to the distance at which it has been placed with respect to the spherical source. So if screen is placed here at say a distance r, then the size of the screen, if it is rho, then x square plus y square is going to be very small in comparison to r. So that is what is the meaning of this. So this approximation which we are using, I mean this representation of spherical wave, will be valid only when we are placing screen at a very large distance in comparison to size of the screen. If you take very large screen, the shape of these you can say the interference rings will be changing. That may be different, but we are not going to discuss that right now, so that is okay for now. There is another assumption which we are making here. So this is that thing that, okay, r is to be very greater than rho. There is another assumption which we are making, that, okay, this a upon r is constant over the size of the screen. Means the amplitude of the spherical wave doesn't change much over the points of observation on the screen. That is also okay to some extent, because, okay, suppose this is the size of the screen, so here r is not changing very much, correct? If r is not changing very much, we can assume a by r to be almost constant. So this will also be keeping our life simple. So that's another thing. Now let us try to do a very systematic analysis. So we have a plane wave which can be represented by this. This is our earlier expression for a plane wave we have already done. And let us assume what we are saying is, okay, that where is the screen? Screen now is at z is equal to r. In earlier case it was at z is equal to 0. So now we are saying, okay, let us say z is equal to r and theta is 0. We are saying plane wave is traveling parallel to the z-axis. I hope you are okay. Let me show you again. So the plane wave is traveling parallel to the z-axis, so theta is 0 here. So in that case, the expression for plane wave will become like this. So there won't be I here, sorry, it was copy paste. So this is the electric field for the plane wave, right? It doesn't have that r dependent component. Similarly, the spherical wave we just obtained is going to look like this. So what do you think is going to be the phase difference? The phase difference you can find out. So see again here, omega t, right? Kr, the term is same. The only term contributing to the phase difference between this plane wave and spherical wave is going to come from this. So that means delta phi rho again is related to that xy thing, is equal to, or approximately, why approximately? Because of that binomial approximation we have used. So this is equal to pi rho square. So pi means we have substituted the value of k. This is 2 pi by lambda. So this is 2 pi by lambda. So 2 cancels with this 2 sitting here. So this is pi rho square, this rho square upon lambda r. So 2 has already gone. That's the phase difference between, say, the plane wave and a spherical wave approaching on the screen at any point rho, and rho is something which is containing that x and y on the screen, correct? So what will be the intensity? Again, that previous expression, I'm not going into that bigger one. So this will be equal to I naught 1 plus, so again that factor of fringe visibility. Actually it was supposed to be here, but we are assuming, okay, let us assume fringe visibility to be 1, then this is just 1, correct? So cos of delta phi, so we just substituted this value. Now there's something interesting here, that intensity as a function of rho, which is of course the function of x and y, uh, rho is nothing but x square plus y square. I hope you remember, right? X square plus y square is equal to rho square. So I as a function of rho is given by this. Now you would see that this is a function, this is a periodic function. One thing is, this is periodic function by virtue of this factor. This is cosine function and is a periodic function. So periodicity is depending upon, so pi is fixed, wavelength of the light is fixed, r, the position of the screen is fixed wherever we have to fix the screen. So rho, so it is the function of rho. Rho is nothing but, rho square is nothing but x square plus y square. So as we keep on increasing rho, oh sorry, let me go back here. Yeah, so rho is something like, okay, x square plus y square. It's like radius of the circle. So as we keep on going away and away from the origin, means we are increasing the rho. And as the rho increases systematically, what will happen? You will be finding intensity to be maximum, then minimum, maximum, minimum, and that is how we will be finding those circular fringes. Why circular? Because the dependence of intensity is only on rho, means only on the length of the radius. It doesn't have angular dependence. It doesn't depend, so it just depends upon radius, rho. It doesn't depend, okay, we are taking radius to this side, or radius to this side, or radius to this side. So that is why for a particular value of radius, intensity is going to remain the same, and that is why we will be observing what? The circular fringes in this case. Now let us obtain the expression for radius of say some mth bright fringe. Okay, the first thing is, okay, what will be at center when rho is 0? It will be a maxima. You can put it here, rho to be 0. So you will be finding I rho will be equal to I naught. Means the central spot will be a maxima, correct? And then let us try to find out the radius of mth bright fringe. So you know, delta phi is equal to 2 pi m. This is the condition for constructive interference. We have already done, right? That the phase difference must be integral multiple of 2 pi. So if we substitute the value of say this is your delta phi here, right? So in this equation I am substituting this condition, so I am finding 2 pi m is equal to this. Simplifying this a little will be giving us 2m lambda r is equal to rho square, and from here we can find out the radius of the bright fringes, mth bright fringe, the first bright fringe, second bright fringe, third bright fringe, and so on. So this will be the radius of the mth bright fringe. So in book this factor of lambda is missing, so that is probably a typo. This must be there, right? So the radius of the bright fringe is going to be given by this. So it is directly proportional to lambda, obviously it is directly proportional to m. So central one is the first one, then is m is equal to 2, the outer one, and so on. I hope I have shown it somewhere. Okay, maybe that's already in the previous slide. So these circular fringes will be actually discussed in context of Fizeau interferometer, which we will be doing in the next classes. And of course these are sort of Newton rings, so circular rings which are formed. So these are called Newton rings. So this is the theory of Newton rings, you would say. So when Newton rings are formed, when a plane wave and a spherical wave superpose or interfere with each other under the conditions which we already stated in our discussion, we will be obtaining the Newton's rings. Okay, so there is another discussion in the book, that what happens when two spherical waves interfere with each other. I leave this discussion to you yourself. You try to go through this and let me know if you are facing difficulties, then we will discuss it. But these two were very important, so I discussed it here. Now we will discuss the concept of temporal weights. Okay, I hope you remember our previous class where we had obtained the expression for intensity in general. This was I1 plus I2, intensity of first source, intensity of second source. In general means the two sources are not necessarily having same frequency. In that case, the resultant intensity is going to be given by this, right? And I think I had discussed it that the two, I mean, you will be finding maxima minima, but the thing will be that these two will not be consistent over the time. So this will be these will be the temporal beats. So that's the term which is leading to the temporal beats. Means if the two sources have slightly different frequencies, there will be temporal beats. Means the intensity will sometime be higher, then it will be decreasing, increasing, decreasing. And the difference is much. If this difference is much, then temporal beats will be very rapid, and we won't be able to observe anything on the screen. Okay, then second thing is this one, the phase differences in the two waves, and we can write down this to be equal to this one. So in that I1 I2 simplified expression comes out to be like this, that again we have put that fringe visibility to be equal to 1, and this omega 1 minus omega 2 is written in terms of this omega 1 is 2 pi nu 1, say this is 2 pi nu 2, so that's what we have done. So this is delta nu and this is delta phi. So that's how we can write down the intensity in general. Means we are not putting any constraint on the source, whether they have to be have same frequency, they have to have a same phase difference or a constant phase difference. There is no condition. In case there is no condition, that will be the expression for the intensity. Now is the concept of coherence. Why is coherence needed? What is the meaning of coherence? Because in your lower classes, I hope you would have heard that to obtain interference pattern, we must have two sources which are coherent, right? But then you should ask question, why is it so? Why they must be coherent? So answer lies here in this expression. Okay, let's assume that the two sources, if they have two different frequencies, if we are using such a sources, then there must be an absolute phase relation between them. Okay, so means to get rid of those temporal beats, what we have to have is that we should take two sources which are having exactly same frequency, first thing. So that is the first condition, that two sources to exhibit stable interference pattern on a screen should have the same frequency. Omega 1, omega 2 must be same to get rid of those temporal beats. Fine. Then second thing, okay, then does it mean that we can have two independent sources having exactly same frequency and get a stable interference pattern on the screen? So the answer to that is no. Why? Because even if we have two different sources having same frequencies, this term means the phase difference between those two sources should remain fixed with time. If we have two independent sources, okay, let me come back. What will happen? We can take those two sources to be made up of, I mean, how is the light coming from the two sources? Each source is emitting its radiation independently, so it may have one say one wave of light which has originated from one source, second wave of light originated from second source. Then it is not necessary that both the waves have been emitted at the same time, and if the two have not been emitted at the same time, we can't expect the phase difference between them to be a fixed one. Okay, suppose two waves came and they will have a given phase difference. The next set of waves, when they will come, they may not be necessarily having the same phase difference as the previous set of waves will be having. So that is why it is very difficult to obtain or maintain this phase difference or phase relation between the two independent sources. That is why we have to reach or to obtain a coherent beam, sorry, to obtain say stable pattern on screen, we have to have two sources which have same frequency and same phase relation between the two. Okay, if the two sources have finite size, so one thing is that okay, there should not be a temporal difference, temporal beats must not be there. And second thing is, if the sources has a finite size, means if you take a slit which is having a finite size, little broader slit, I think one of the student asked this question, So if we take a slit or the sources of finite size, it can be considered to be composed of number of spatially separated independently radiating point sources. So a finite size source can be considered to be made up of so many tiny point sources, and each source is radiating independently. Correct? So if this will happen, what will happen? In that case, again, we won't be able to see this phase relation between those two or those multiple independent point sources. So that is why the size of the slit must be very small, plus and these two aspects, this temporal beat and this phase relation, maintaining the fixed phase relation, comes or makes the part of what we call the spatial and temporal coherence of the source. So basically, to obtain stable interference pattern on a screen, the two sources of light must be spatially coherent, means they should be very small in size, and means, okay, whatever is the uh, region from which the radiation is coming out, means source or the size of the source, from the all points of that region, the radiation coming out should be having a fixed phase difference or fixed phase relation. That is what refers to the spatial coherence. Second is temporal coherence. So means their frequency difference should not be very large. So the radiations should preferably be monochromatic. That is the second condition for obtaining stable interference fringes. I am repeating, stable interference fringes on the screen. Otherwise you may see the interference fringes on the screen, but they won't be stable over the time. So we won't be able to see, okay, if there is some maxima or a minima, something which may be maxima at one point of time, maybe a minima after some other point of time. And if the frequency is so fast, you would be probably able to identify what is going on the screen. So that is why, to see the stable interference pattern on the screen, these spatial and temporal coherence must be satisfied, and that is why we say, okay, and if the spatial and temporal coherence is not there, what will happen? The visibility of the fringes, that gamma factor, at different points on the screen will be affected, and this is what is known as the fringe localization. Means you will have at some point fringe visible, at some other point it is not visible, and so on. That's called fringe localization. So we are not going into details of this. We are right now interested in obtaining the stable interference fringes on the screen, so that's okay. So to obtain, that is why, to obtain stable fringes on say fringes on the screen, one needs to obtain coherent sources of the interfering radiation. So two radiations which are interfering, we must have two coherent sources. And to obtain coherent sources, there are two general methods. One is by division of the wavefront. Second one is by division of the amplitude. So I think that's more than sufficient for today. I will stop here. In next classes, we will discuss division, how we can obtain interference pattern by wavefront, by the division of wavefront, and maybe in the next to that we will be discussing how we can obtain interference pattern from the division of the amplitudes. Till then, thank you very much. Stay safe. If you have any doubts or questions, please feel free to contact me. Thank you very much.